Let's start. Yeah. So in week 5 directory, you can see the ROP challenges are rop-5 for 32 and 64 for here, and then rop-6 for 64. And today we will start with the rop-5-32. And this challenge, what it does is here in the main function, it calls the input function, and it reads more than the buffer, the 4 times more than the buffer size. Yeah, so there's a buffer overflow. But some of the functions that we can reuse. So because this machine is enabled with ASRL, you don't know where the other library functions are. So you cannot directly call execve or open or other system call here, because it only has like the string copy function here, PRCTL, which you don't need maybe. And also it has an input function read, puts, printf, pop all dx, but then nothing about like the open the flag file, or execve to execute the shell or system, those kind of functions. These are not existing in the binary. So if we get into the binary from the functions that we can reuse, these are just like the main input, the string copy, or like the printf, puts, read, that's it. So there's no function that we can reuse for the execution or opening the file. And what we will do is we will try to leak the address of the printf from the printf plt linked, the address link that here. So for example, if we disassemble the address, then it will show that like it will jump to the GOT entry of the printf. So for example, this is the GOT entry of the printf. So it will call some of the function. It will resolve the function in the libc by using the string printf. And then after that, it will put the address of the printf function in the library at here. So what we can do is we can leak this address and then read that from the program's output. And then we can exploit the vulnerability again to use that as like by calculating the offset between the execve and the printf. And then we can translate the printf address into the real library execve address. Then we can directly call that function. So we will do the exploit like that. And to get into the exploit condition, so the read function is here, and our buffer is like the EBP minus 0x88. So after knowing this, let's try to exploit this challenge. So from pawn, import all. Then we will run the process rop-5-32. Then we will send the buffer as a multiplied by 0x88. And then save the EBP. And we can call some of the functions here. And to call some of the functions, we need to have some rop gadget. So we will generate the rop gadget into the rop.txt, and then open that in here. Then in 32-bit return-oriented program, we are focused on like the some number of pops and then return. So our interested instructions are around here. So we have some of the pop return, pop return, pop return. So some of the many pops and returns are here. So we can copy from here to there. And let's collect our rop gadget addresses. So pop return is at here. So it will pop EBP and return. Pop return is here. Pop return. So we can copy this address to here. Pop, pop, pop return is here. And we have 4 pops and return here. So we also have the gadget for the 4 arguments function. So we can collect the gadgets like this. And then our first function call will be the printf. But how we will get the address of the printf is, so we will first get the address of the printf PLT. That's at the p.elf symbols printf. So if we look for the symbol in the binary program itself, then it will tell us like where the printf PLT, the precision linkage table is. Because at the binary, we can know the address of this one, but we cannot know the address of their library function because that is determined by at the runtime. Yeah. So it'll just tell the printf PLT, but using printf PLT, we can call the function. So we can put p32 address printf PLT, and this will call the printf function. And then we want to call another function after printf, and then printf has 1 argument. So we will put 1 argument here, and then in that case we can put pop return, and then for the first argument of the printf, what we will do is we will print up the printf GOT. So it will just leak the data, store that the GOT of the printf, which is the address of the printf in the library space. So we will call this, and then to get the address of the GOT of the printf, so address printf GOT, then p.elf GOT printf. And it will give the address of the global offset table that stores the function address. So then by calling this, it will leak the address, and then you can return to the input function again, because we want to use this leaked value and then calculate that to translate the printf address into the exact VE address, and then use that as a new address for the exploitation. So what we will do is we need to get the address of the input function, and that is in the program. So we can access from the p.elf symbols. And we will call input function again. And important thing is that after we run the process, we can receive 1 line. So I will just run the program, and it prints out 1 line. And then after I send the data, then it will print another line. Yeah. So it prints 1 line, and then after I send the buffer, then it will print out 1 more line. Then so basically it will print so it has a 2 printf. So what is that is from the input function. So we overflow at this part, and then the printf in the program will print out the hello, my input, and then this new line. Then that will be received by this receive line. And then there will be another printf call. So because this input function will return to the address of the printf PLT, because we will send the overflow vector at here. So it will call printf, the printf GOT. So we can receive another data at here as the address of the printf. And then it will return to the pop return. So it will return to the input function again. So after this receive, we can exploit this vulnerability again. And then next time we can use the address of the exact VE. So to do that, so then I will receive another data. Then this will be can print it as a data. Let's as like this. So what it just did is like it send our exploit vector and then calling the printf GOT and then return to the input function again. So it says like, please type your name again because it has executed it again. But we have some of the data received from the program, and then some part of this data will store the library address, the printf function address in the library, because we leaked the global offset table of the printf. So let's examine what's in this data. So to do that, we can split this data into 4-byte chunk. Because like in 32-bit machine, we regard the 4-byte as a minimal unit for the registers. So we will split the data into 4-byte chunk. And how we can do that is for I and data. The chunk, then the U32 chunk. This will change the item to the integer. Then we can create an array. Then for item an array. So we can interpret the data as a 4-byte as a chunk, and then so my bad, array is not. So I define the array as a ARR. This. And this data can be split into 4 bytes like this. Yeah. And then some part of this will store the address of the printf. But how can we identify the address of the printf? So to do that, we can first get an instance of the printf address in the library space. For example, if we break a main and then run the program and print printf, then we can get an instance of the randomized address in the library space of the printf address. Yeah, here. So although like the top 5 digits may be changing for the multiple randomization at each time of the running, but it's least 3 digits. These 3 digits will not be changing because that's the offset within the page. And then these kind of the libraries are like the mapped in the page boundary. Yeah. So it's aligned with the page. So these 3 digits will never change. So if you can find something starting with the F7 and then that ends with the 680, then it's the address of the printer. So F7, 680, memorize that. Then try to execute this exploit again, and then can you see like the F7 and 680 here? So here's F7, and then here's a 680. Yeah, maybe there's a little shift in the data. So if we can identify like the F7 680, then like, that's definitely some of the address. But I think like this is the 1 byte shifted, so F7 is at the end, but it should come at the front. So what we can do is we can do a little offset here. So offset is 1, and then add an offset to the data. Then we can run it again. Then we can see that F7 something 680, F7 something 680 at the fixed location of the leaked data. So we can safely assume that this is the data that we leaked from the printf GOT. So that's the address of the printf. So that means the array 0, 1, 2. So we have an address of the printf in libc as a array 2. Yeah. Now we have the address of the printf. And then to calculate the offset. So what we will do is we can call exec v, yeah, and then we will call exec v -h 0, 0. And then to do that, in doing that, we need to calculate the distance between the printf and then execb. And to calculate that, we can run the LDD to check which library file it loads. So the library file that the binary loads is this one. And then we can open an ELF object of the file like this. The E dot symbols printf is the address where the printf is. So offset printf is this one. Offset exec v is EDA symbols exec v. Then after getting these offset, so we can get the address of the exec v in libc by address of the printf libc minus offset printf plus offset exec v, because the relative offset between the printf and then exec v will be the fixed one. So we can calculate the address of the exec v in libc like this. And then now this is the second time we send the buffer. So we know that the vulnerability is at the EBP minus 0x88. And then we can fill the saved EBP as something else. And then at this time, we want to call exec v libc directly, because we leak the address of the printf here, and then use that to calculate this address, so we can directly call the exec v. And then we don't care about this one, but we can put pop return, because we will have the 3 arguments, and then p32 plus p32 0. So the second and third argument will be the 0 for the exec v, but for the first argument, we need to find the string. And one of the easy way to find the string is that now we know that this binary program is a non-PIE, so we can reuse the fixed code address area, and then in the GDB break and main and run it. And then if you print out some of the strings from the 8048000, which is the start of the code section, then you can find this address, the number 4 as a string. So it's an easy one. So that's at the address 8048028. So address of 4 is at here. So we can call exec v 400 here. Yeah. And then to run the 4 file as an executable, I will create the 4.c. Then I will just insert a visual cue that this program is running. Then set regid, get regid, and exec v says 0, 0. Then I will build this file. So now we have a binary 4. So if we run this, then it will say exploit is running, and then run the shell. Right now it's not in the exploit context, so we cannot get the privilege. But if we run the EDA-PI, so right now I didn't send the output. Then pdot interactive. So what we will do is, so we will first run printf to leak the address, and then calculate the address of the exec v from the offset, and then use that address to run, execute this file. Then finally, we will get the shell. So it says exploit is running, then we can get the group ID of this one. Yeah. So any question about the exploiting this one? So this one is very similar to the ASLR4 challenge. So in that challenge, the challenge directly tells you where the address of the printf is. But in this case, you can reuse some of the function in the code area, such as a printf, to leak the address of the printf function itself. And then you can calculate the where the execve function is from the getting the offset of those functions in the libc. Then you can finally get the translate the address of the printf into execve, then run that function. Any questions about this exploit? So for 64-bit, you can apply the similar challenge, but you would like to align the pointers in 8 bytes granularity. So the reason why I choose 4-byte granularity here is that because we are attacking a 32-bit machine. So that's why I choose 4-byte, but there could be a misalignment. So you can choose the offset 1, 2, 3, 4, 5, 6, 7. Then you can eventually find which one is the correct address for the printf. And then for the 32-bit, we just focus on the F7 680 as something unchanging the printf address. And then in case of the 64-bit machine. So if we get an instance of the printf, yeah. So the first 7F will not be changing, but this also, the last 3 digits, 810, will not be changing. So you can focus on the 7F and 810, yeah, for finding which one in the output is the address of the printf. And then from there, you can get that output and calculate the exact BE. Then you can call that as a function. All right, if there's a no question, then I will move on to the rop-6-64. So the challenge itself is not that new. So it's just has an input function, and then it will have a buffer overflow it here. So it gets more than the buffer size. Yeah, so there's just an overflow, but you can execute the exact BE because the binary program itself has it. So you can run it, but the problem is that it doesn't allow you to set the third argument. The problem is, so for calling execve, so we need to set the first, second, third argument, RDI, RSI, and RDX. But the problem is that if we get the wrap gadget for this binary program, so if we move to some of the pop instructions, so we have pop these instructions, but RDI and RSI, but we don't have a pop RDX. Yeah. So because there's no pop RDX instructions, you cannot set the register value for the third argument, so you cannot run execve. So I will show you that why you cannot run it by just setting first 2 arguments of the execve. So I will try to call that function, and then let's see in the debugger first. So to use the debugger, I will copy rop-6-64 to rop-6-6x, and then we'll create the e.py. Download this, and then context. So we use Tmux. Split window, horizontal split. And then we would like to set the breakpoint So at the return of the input function, we will set the breakpoint, because that's where our return-oriented programming chain starts. So we will ignore what we received, and then we will just call. So this is a read function, and then the second argument is coming from RSI, RAX. So the buffer, our buffer is at like a RBP minus 0x80. So we can fill 0x80 of A, and then for the save the EVP, we just fill the B's. And then what we want to do is we want to call execve some of the string as an argument, maybe 4, 0, 0. Yeah. And let's try to find some of the useful string in 64-bit 1. So break and main, run it, and then 20s 0x400000 for this one. So at here, yeah, we have at this address, we have an @ sign here, so we can use that as a string. So let's use this as a string. So we will try to run this. And then p.elf the symbols. And then because the program itself has an execve, so we can get the address of the execve plt. Then we can call that function. Then we will call that function. Then before calling that, we need to set the argument. And to set the argument, we need to get the rop chain. So we have several pops and returns here. Several pops here. So I will copy these chunks to here. And then we have a pop RDI return at here. Pop RSI R15 return is at here. And we don't have a pop RDX at all, but I will just try to run exactly with just popping these two arguments. So buffer as a p64 pop RDI return. Then we will use the address of the 4. So I didn't create that one, not the 4. The address of the @ sign is at here. Yeah. And then we will set the address of the @ to the first as a first argument, pop RDI by pop RDI and return the @. And then we will call p64 pop RSI R15 return. Then RSI as a 0, then R15 as a 0, then we can run execve. And we can send this as an exploit, then wait. And now we can see how this execution will flow through. So let's execute the program. And then now our debugger is stopped at the end of the input function. So it will first return to the pop RDI, and then the RDI value we will pop is the 400020, which is a string @. Yeah. So we will run pop RDI. Yeah. And then return, and then pop RSI return. Yeah. R15 return. So what it does is, so it changes the RDI value as a 40020, and then it will run the pop RSI. So RSI value as a 0, and then R15, and then, so the R15 is a 02, and then return. Then it will return to the execve. But right now, we just call the exec BE, but its first argument is RDI, the at. Second argument is RSI, 0. But the third argument is a 1000. So this is not a valid address, but in such a case, what will happen? So if we just follow the exec BE and then the resolver runtime, yeah, and then it will eventually call the exec BE function. And then if we just run until the return, then it will generate some of the error code and then jump to the invalid address because our execve call has failed. And then let's see this in a more pretty way. So that means I will just generate an output as an exploit.txt. So I will write out this as into the buffer. So we have then exploit.txt. And then what I will do is run schase with rop-6-64 and then exploit.txt as its input. Then we will see that it runs execve at as we run the exploit. But the problem is that this one is okay, but these for this variable. So we didn't put the some of the address as some of the valid address, nor the 0. So it will regard this as an invalid address, so the system call will fail. So we need to set the third argument value as a 0 to run the execve correctly. Then how can you set that? So the problem is that we don't have any kind of the pop RDX here. Is that an end game? That's not true. And then what you can reuse is that, so in the most of the C program, because it should follow the C standard. So in info functions, you can see that there is a libc csu init function. So if you disassemble this one, then you can see lots of pops and then return instruction here. And then another interesting instruction is setting the R13, R13, 14, 15, and then call this one with the R12. So that we will use like these instructions as a gadgets to set the value of the RDX from R13, because we can change R13 at here. Yeah. So by using this gadget, these two parts of the gadget, we can set all the arguments and then call the execve. So we will do that. And then to do that, we need some more gadgets. So now it's pretty, and then we will have some more gadgets like this. And what we will gonna do is we will return to this one. So if we return to pop all return as this one. So it's not actually pop all registers, but all the registers from RVX to BP 12, 13, 14, and 15. And then we can set the P64 pop all return. And then, so for this one, we can put the address of so it will pop RDX first, then RBP next, and then R12, R13, and R14, and R15. And then we can set all the values of this one. Then what we will do is for RBX, we will set it as a 0 because this is used as an index for the accessing R12. To simplify the problem, so we will just set the index as a 0. And then for RBP, we don't care, so we set it as a 0. And then R12, we will set it later. So just put 1, but we will set that as a sum of the address that we can call the function on. And then for R13, that will be delivered to the RDX. So the third argument, so RDX, and then third argument. So we can set it as a 0. And then R14, it goes to the RSI, the second argument. So we set it as a 0. So it goes to the RSI, the second argument, 0. And then the first argument will be R15. So we need to set it as a sum of the RDX, sum of the first argument value, because that the lower part of that value will be delivered to here. So if we set it as a R15 to be the same value of the RDX, then this instruction is quite meaningless. So that we can nullify the meaning of the running this instruction and then still put the RDI value, the first argument value at here. So what we can do is we can put the target of the RDI here. And then we can put the address of some function address here. Then it will call the function. So referring to the R12, but the RBX is a 0. And then it will call the function pointer stored in the address R12. So that we can compose an exploit like this. Yeah. And then the target address of the RDI, we have the address of at here. So because we will just call execBE at 00, so we can use that address. So here the RDI target address is address of at. And also before running this, we can run p64 pop RDI return to set the value of the RDI as an address of at. So by doing this, the RDI and the R15 value will be the same, so that this instruction will be nullified. And then it will call the address of the sum of the address that storing the function address. So for this address, we need a function address that stores we need an address that stores the execBE function address. Then that actually found by the execBE GOT, because that's supposed to storing the address of the execBE in the library space. So we can write a variable, and then we can find the elf.got. So we can get the GOT entry of the execBE. Then we can put the address of execBE GOT entry at here. So we will not run this simple execBE exploit, but in this case, we will run the execBE exploit with this kind of the weird instruction. And then after popping all addresses like this, and then we would like to run this gadget. So we need to put this call instruction is at here. So we want to return to 64 call instruction. And let's debug this and then follow the instruction if it sets all the values correctly, and then call the function. So I will run the exploit. Then now it breaks at the end of the input function. So the first instruction is that pop RDI and return. So it will set the RDI as the address of the app as the first argument. And then it will return to pop RBX, set RBX as a 0, and then RBP, set RBP as a 0. And then R12 is the value of the GOT of the execBE. So it will store the address of the execBE here. Yeah. And then it will pop R13. And then R13 value is 0, which will be passed to the RDX, the third argument. And then R14, the second argument, which will be passed to RSI, yeah, will be 0. And then for R15, we will set the same address of the RDI. So R15 and RDI are the same, pointing to the address of the add. And then it will move to these instructions. So it will run R13 to RDX. So now, finally, our third argument set as a 0. And then R14 moves to RSI. So right now, the RSI is a weird value, but it will be set as a 0. Then it will move lower part of the R15D to EDI, but both values are the same. So the next instruction has no effect at all. And then it will call R12. RBX is 0, so the just value in the R12 with the argument of at 0, 0. And then it has no fourth argument, so we can ignore RCX. So it seems it calls the exact VE, but let's follow it. So to do that, we need to do SI because we need to follow the call. So it calls the exact VE, then it resolves the address of the exact VE, and then it will finally call the exact VE. And then what is the first argument? RDI at. Second argument, RSI 0. Third argument, RDX 0. So it called exact VE at 0, 0. Yeah. So by controlling, by the mixing the lots of pops and then moving some of the instructions connected with the call instructions, so that we can link the gadgets like this to call the address of the EXECV directly at here. And then in this case, we don't have to think about the ASR at all, because if we know the GOT entry of the EXECV, then we can exploit this. So to follow this with the strace, so I can put the exploit.txt like this. Then now it runs the exact VE at null null. But right now the error message is there's no such file in the directory. So what I can do is I can create the file. So for example, at.c. And in this C file, set regid, get regid. And then print out just make this, and then if I run it, then it says something like this, and then it will run a shell. But at this time, I will run it to the rop-6-64 with the exploit.txt. Then it says exploit successful. So if I do exploit.txt, and we can get the shell by chaining the pop many register gadgets and some of the call gadgets that can transfer the register value to the RDX. So the rop-6 challenge is basically about even if you do not have a pop RDX, there's a way that you can set the other register values and finally set the register value for the RDX by using some pop other registers and then move that register to the RDX. So you can creatively find any kind of the code in the primary program as a gadget and utilize that in this manner. Any question for the rop-6 challenge? So the interesting part was okay, there's no pop RDX at all here, but we can link pop R13 here and moving that to RDX, and also RSI, EDI. So we can set 3 arguments and then call exactly. So any questions? So why can you get the shell without running e.py? That was the question. And then if you take a look at the e.py, so after building all the buffer, I wrote it to the exploit.txt. And then what I did is the command like this. So it will output the entire exploit.txt to the program first, and then it will get my input and then just use that as an output. So if we do cat, then it will just echo what I type. So if I do this, it will send the exploit.txt first, and then it will wait for getting my input. So that's why it worked. And then the same thing could be done by changing. So I will not attach GDB at this point, but changing this to 64, and you can get the shell here. Right. So it's a little sophisticated attack in terms of how you can link those two instructions to run the execve. But basically, this challenge teaches you if you have a something gadget, then linking them together, then you can create some new gadgets that has a new capability. So even if you don't have a certain the direct gadget, yeah, don't give up. That's the lesson in this challenge. Any other questions? All right, if there's no more question, let's finish the tutorial today here. And I will post this video in a few hours. Yeah. And thank you for your attention, and feel free to leave any questions on Discord. Yeah. And we will have a new challenge set releasing next Tuesday.
By the way,
right.
Professor, can I have a
Yes.
question about the 1-byte codes dash 32?
Yes, you can ask questions for that.
Yeah, actually, 2-byte I will done. So yeah, but when I see the 1-byte code dash 32, actually I did what you give me an advice for. I use the 46 as a operand. But one of the most problem is when I see the code CD80. Actually, when I get four additional F, they separate my precious CD80, so
yes.
it doesn't work.
Yes.
So in the case, I think that I have no idea how can it can get better. Yeah, because except those system call, I can apply, I can manipulate do that, but especially for the system call, it seems like it's impossible to eliminate 46.
So, for example, in the case of you wrote the alphanumeric shellcode, so you can create a CD80, yeah, even if you don't have a CD80 characters, right?
Yep.
So and this kind of the adding F character in between each character of your shellcode happening before running your shellcode. So what you can do is you can change the 46 to 46, which is an F character, to the 80 at the runtime. So you can write it as a self-modifying code. And eventually it will run the CD80, not the CD46.
Yeah, it works. Yeah, that sounds great. But even if so, yeah, this is because I think so. I think so.
Yes.
Okay, I try. Thank you.
Yes. So it requires a little bit more sophisticated method, but it will work. Yeah.
Thank you, Professor.
Yeah. All right. Yeah. For all the others, don't forget to challenge to the extracted one. These are on the the VMCTF1 server, and then that will be fun too. Right. Let's finish tutorial here. Yeah. Then thank